All right, there we go. Example problem number 4, an inclined plane. We did an inclined plane before in the previous lesson when everything was in equilibrium. This time it's accelerating down the ramp. Same rules apply. Things, what do we have here? We've got a 5 kilogram mass sitting on a ramp. Right, we'll rotate that a little bit. So this is a 5 kilogram mass sitting on some ramp. The ramp is inclined to the ground at an angle of 37 degrees. Or am I writing 39.7? 37 degrees. Interesting. Okay, so that's where that's set up, 37 degrees. And the coefficient of friction between the ground of the ramp itself and the block, mu k 0.2. And we are told the block is accelerating that way. So that's what we know. It's moving down the ramp at 37, inclined to 37 degrees, all good. First things first, always do this. First is draw the free body diagram. What forces are acting on it? Well, gravity pulls it down, always. Straight down. Always straight down. The force of gravity is calculated by the mass multiplied by the acceleration of gravity, which is 5 kilograms multiplied by the acceleration of the gravity on planet Earth is 9.8 meters per second squared. 49 newtons. Now, it's accelerating down the ramp. You're told there's a coefficient of friction between the two. So there's a force of friction. If it's moving down the ramp, the force of friction is up the ramp. We don't know what that is yet, but it's in that direction. Always opposing motion. If it's accelerating and moving, I should say if its motion is down the ramp, the acceleration is up the ramp. And it's not moving towards the center of the earth or straight down towards the center of the earth. It's sliding down the ramp. So the ramp itself is pushing up. The ramp is supporting some of this block. And the ramp's force is always, the ramp can't push up. The ramp can only push perpendicular to itself. That's why we call that support force the normal force. Thank you. You can put them anywhere. Thank you very much. All right. Just got a delivery. All right. So here we go. There's your free body diagram. Now, what's next? Determine the force of friction. Well, before we actually calculate any more forces, one thing I want to reiterate is that anytime you have a ramp problem, instead of having our x and y axes the way we're used to, right? We're typically used to this, x-axis, y-axis. Now we're going to rotate things. We're going to rotate things to make our y-axis this way and our x-axis this way. Oh my gosh. Good. Now, that's really, really important because if we make our x-axis and y-axis like that, let's see if we can make these different colors here. Let's see. Like so. And we take them and put them here. Well, now our friction force is in our x-axis, our normal force is in our y-axis. The only force that doesn't match up is the force of gravity. That's really, really very useful. So if we make our axes, by rotating our axes this way to make that our x and that our y, just by rotating it this way a little bit, actually exactly 37 degrees, since the incline is tilted 37 degrees. If we rotate it 37 degrees, now we do some of the forces in the x, some of the forces in the y, this way, this new y, that new x, life is much simpler. It's accelerating in the x-axis. It's not accelerating in the y-axis. So that's very useful. Sum of the forces in the y equals ma, but it's not accelerating in the y direction. It's accelerating in the x direction. So what forces are in the y direction? The normal force is in our new y direction, right? Our new y direction is this way. Our new y direction is this way. That's our y direction. This is going to be our x direction. Our new y direction has got the normal force. But remember, we also have that gravity force, and some of this gravity force, gravity is straight down. Our x-axis is this way. Our y-axis is this way. This angle is 37 degrees. So we're going to take that force of gravity, which is going to become the hypotenuse of our triangle, and we're going to split it into two pieces. Some of that is this way. That's going to be the adjacent side. And some of that is this way. That's opposite 37. This has become the opposite. So now we've got a right triangle, adjacent, opposite, hypotenuse. There's our 37 degrees. This side here, if this is 49 newtons, right? This number here is 49 newtons. This number here, the adjacent side, is going to be 49 newtons adjacent. So katoa, cosine of 37 degrees. This here is the sine, right? So sine, opposite over hypotenuse. This side here is going to be calculated by the 49 newtons times the sine of 37 degrees. All right, doing some math. 49 times the cosine of 37. Cosine of 37 is just about 0.8. 37 cosine times 49 is like 39.1. So this is going to be 39.1 newtons. So we come back here, sum of forces not, that minus 39.1 newtons equals 0 because it's not accelerating in the y direction. That's 0, so anything times 0 is 0. So that's going to tell us the normal force is 39.1 newtons. What minus 39.1 equals 0? 39.1 equals 0. So now we know the normal force. That's very useful. That allows us to calculate the force of friction. You need the normal force to calculate the force of friction. When we go to do the next part, sum of the forces in the x direction, well, force of friction, we'll call force of friction positive this time. That's towards the upward direction, minus a piece of this gravity part here, minus this part, minus some of the gravity. The sum of the gravity, well, 49 newtons times the sine of 37 is the gravity that's down the ramp. Sine of 37 degrees is just about 0.6 times 49. That gives you 29.5 newtons. So this piece is 29.5 newtons. So we've got the friction up the ramp, 29.5 newtons down the ramp. Equals MA. The force of friction minus 29.5 newtons equals 5 kilograms times. We need to calculate the force of friction. How do we calculate the force of friction? force of friction, very important you remember this, the force of friction equals mu times the normal force. You were told the kinetic friction, the coefficient of kinetic friction is 0.2. We just figured out the normal force to be 39.1 newtons. Multiply 0.2 times 39.1. The force of friction equals 7.82 newtons. So that's very useful. Now we know this. 7.82 newtons minus 29.5 newtons equals 5 kilograms times A. 7.82 minus 29.5 negative 21.68 equals 5 kilograms times A. Divide both sides by 5. That's also newtons. A newton divided by a kilogram. So that divided by 5 gives you 4.33. The acceleration equals negative 4.3 meters per second squared. Did we solve all the things we wanted to know? We drew a free body diagram. We determined the force of friction to be 7.8. That was this one. We got the force of friction, we got the acceleration, and we did the free body diagram. All done. The key to that whole thing is rotating your axes. Figuring out the forces up the ramp compared to the forces down the ramp, the forces perpendicular to the ramp. And so you only have to take the gravity and split the gravity into its x and y components. That's the hardest part. But once you get that, it's simple.